Suppose we have a voltage that we refer to as the input. Suppose we want to multiply this input by a number to produce another voltage that we'll refer to as the output. Or, suppose that we have several input voltages, and we wish to add them together, and we want the output voltage to represent their sum. Operations such as these, as well as many far more advanced calculations, can be performed with circuits that have what we call an operational amplifier, typically referred to as an op-amp. In this video, we'll discuss circuits that have an ideal op-amp. An op-amp has 2 input terminals and 1 output terminal. The op-amp also has 2 terminals for providing power to the device. Current can never flow into or out of the input terminals. Current can flow into and out of the output terminal. The current that flows into or out of the output is supplied by the 2 terminals providing power to the op-amp. The 2 terminals providing power to the op-amp are typically not shown. But it's important to keep in mind that the op-amp only has the ability to produce output voltages that are in between the voltages of the 2 power terminals. One of the 2 inputs has a plus sign next to it, and the other input has a minus sign next to it. The op-amp takes the voltage value of the plus input and subtracts from it the voltage value of the minus input. The op-amp then takes this difference between the 2 input voltages and multiplies it by a very large number. The op-amp then tries to make the output voltage equal to the value of this result. This means that if the plus input is even slightly lower than the minus input, the op-amp will try to make the output voltage equal to the largest negative number it is capable of producing. And if the plus input is slightly higher than the minus input, the op-amp will try to make the output voltage equal to the largest positive number it's capable of producing. Now, suppose we do something that we call providing negative feedback. These 2 resistors cause a portion of the output voltage to be added to the value of the op-amp's minus input terminal. Suppose that the voltage of the op-amp's plus input terminal is lower than the value of the op-amp's minus input terminal. This will cause the op-amp to want to decrease the voltage value of the output terminal, which will then also end up decreasing the voltage of the op-amp's minus input terminal. The output voltage will stop decreasing when the op-amp's minus input terminal is almost exactly equal to the value of the op-amp's plus input terminal. Now, let's consider a new scenario. Suppose that the voltage of the op-amp's plus input terminal is higher than the value of the op-amp's minus input terminal. This will cause the op-amp to increase the voltage value of the output terminal, which will then also end up increasing the voltage of the op-amp's minus input terminal. The output voltage will stop increasing when the op-amp's minus input terminal is almost exactly equal to the value of the op-amp's plus input terminal. Therefore, the presence of negative feedback always forces the op-amp's 2 input terminals to always be at almost the same voltage value. Once the voltages of the op-amp's two input terminals are almost at the same value, the difference between them is a very small number. The output voltage is then this very small number multiplied by a very large number. For this example, let's suppose that the value of the op-amp's plus input terminal is always set to 0 volts. The negative feedback will force the op-amp's minus input terminal to also always be set to close to 0 volts. Let's define this point here as the input of the circuit. If we apply a voltage to this input, a current will flow. Since current is unable to flow into or out of the op-amp's input terminals, the value of current that flows through the first resistor must also be the exact same value of current that flows through the second resistor. The voltage drop across each resistor is the value of this current multiplied by the resistor's resistance. Now, let's suppose that one of the resistors has a larger value, which we'll represent as two resistors in series. Now, the magnitude of output voltage is changed as shown. If we want the output voltage to be positive when the input voltage is positive, then we can change the location of the input voltage as shown. Our circuits can have several different inputs. Since current can't flow into the op-amp's input terminals, this means that the current through the resistor on the right is equal to the sum of the current flowing through the other three resistors. The voltage drop of the resistor on the right is the sum of all these currents multiplied by the resistor's resistance. The output voltage therefore represents the sum of all the input voltages. Suppose we use a capacitor in the circuit as shown. The output voltage represents the integral of the input voltage waveform with respect to time. Suppose we swap the positions of the resistor and the capacitor. The output voltage represents the derivative of the input voltage waveform with respect to time. Another important use of op amps is to act as a buffer. In this case, the output voltage is exactly equal to the input voltage. Although no current is ever drawn from the input, the output terminal supplies a current coming from the op amp's power terminals. Much more information about electric circuits is available in the other videos on this channel. Please subscribe for notifications when new videos are ready.